Welcome back, guys. And so this is now part 3 of the organic chemistry series. And within this part, we're going to cover alcohols. We saw in part 2 how we can convert ethene, so we can convert an alkene to an alcohol by applying basically reacting the alkene with steam and with a catalyst. And we can do an addition reaction, which adds a hydrogen to one of the carbons and adds an OH, an hydroxyl group, which is composed of an oxygen and a hydrogen to the other carbon. And this is sort of what the molecule looks like. So this is ethanol, eth because 2 carbons, and ol is the suffix for any alcohol molecule. So here it is. This is what it looks like. So I've got my 2 carbons here. They're all attached to at least 1 hydrogen. And as you can see, this second carbon is attached to 1 oxygen. And then the oxygen is bonded to a hydrogen. And this is the OH, the oxygen-hydrogen functional group. This OH group comes with its own set of reactivity, its own reactive sort of profile, and it can do a lot more different reactions because now we have the addition of the oxygen within the compound. So alcohols, opening a whole new set of functions or reactions. So alcohols have an OH attached to at least one of the carbons in the chain. They react similarly regardless of the number of carbons, hence they are a homologous series of compounds. So I've mentioned this concept before of a homologous compound series. It just means that in this set of compounds, regardless of how long the chain becomes, once we have this OH group, they all will react similarly to a certain extent. So just a small little meme for you. I have a fear of hydroxyl groups, therapist. Oh, me. Thought I'd throw that in there. Anyway, so the general formula for an alcohol is CN2N plus 1 OH. So let's draw the first 4 alcohols and their chemical formula with the equation. So with methanol, I have 1 and I need to have an OH, and then I need to fill in the rest of the bonds to make sure that the carbon in the center has 4. That's methanol. Methanol, we have to have 2 here. One of these carbons has to have the OH, and then we just fill in all of the other bonds with hydrogens. And it's quite self-explanatory again with propanol, and with butanol. You just got to make sure that one of the carbons within the backbone is bonded to the OH. And honestly, you can have this OH, you can have it bonded to this carbon here, you could have put it to this carbon there, or you could put it on the end there. But at least one of them should be bonded to this OH group. The other way you can draw this OH is if you can draw that bond separately, the OH bond there. But if you just draw them together like that, that's completely fine as well. Unless the question specifies to show all bonds, draw the OH like that. If not, then you can just have it there on the end. In terms of using this formula here, so N is the number of carbons. So if I use the formula here to work out what methanol is, so that's going to be C, that's going to be H. 2 times 1 is 2, plus 2 is 3, so CH3OH. So that would be the formula for methanol. If we work it out for ethanol, so N is 2, so C2, 2N plus 1 is going to be 5 OH. With propanol, 2N plus 1, 7, that's going to be C3, H7 OH. And if we work it out for butanol, that's going to be 9, C4, H9 OH. Like so. Quick and easy. So, the first 4 alcohols have similar properties. The first property, they are flammable. Something is flammable means it burns quite easily and it will undergo combustion. So let's write a balanced chemical equation for the complete combustion of ethanol. So we have ethanol, one second. So for methanol, so that's C2H5OH, which we can derive from up here. And combustion, which means we have oxygen and we're going to make carbon dioxide and H2O. Going about it the same method that we always use. So we have left-hand side, right-hand side, CHO, like that. So on left-hand side, we have 2 carbons, only 1 on the right-hand side. We have 6 hydrogens on the left, and we have 3 oxygens. On the right, we have 3 oxygens and we have 2 hydrogens. The first thing we're going to do is balance out the hydrogens on this side. So I'm going to pop a 3 over there. That changes the hydrogen count to 6 and changes the oxygen count to 5. Second thing we're going to do is we're going to change the carbon count. That's going to make that 2. And that's going to make that 4 plus 3, which is 7. And then the final thing that we're going to do is we're going to balance out the oxygens. So to balance out the oxygens, we just put a 3 over here, which changes it to 6 plus the 1 there. That's 7 oxygens. And that's a balanced equation for the complete combustion of ethanol. So the second property, after being very flammable, we have methanol, ethanol, and propanol, as well as butanol. They are all soluble in water with a neutral pH. That means they dissolve in water, and the solution that they make as a result is neutral. So around pH 7. So roughly, I would say, approximately. These alcoholic compounds will all react with sodium, and hydrogen will be one of the products. So hydrogen gas. And we can convert alcohols into something called a carboxylic acid. So we can go from alcohol to a particular type of acid. For example, methanol. So alcohol with 1 carbon can be turned into methanoic acid. And then we have ethanol, which can be converted to ethanoic acid. And this will then relate to the next part within the organic chemistry series, where we will talk about these carboxylic acids. Now, a few uses. So we can use alcohols as solvents because they can dissolve many things that water can, but they can also dissolve things that water can't. Things like fat, oil, and other hydrocarbons. And the first 4 alcohols can be used as fuels. They can be burnt. Like ethanol is used in spirit burners, and they burn quite cleanly. They don't really have a particular scent when they're burnt. So if we look at these photos here, this is water with oil, and you can see like the separation here. If I wanted to dissolve this, I could add in some ethanol or any other alcohol for that matter, and it would help dissolve the fat. It help dissolve this oily layer and help both of them sort of mix better, because the alcohol will also dissolve in the water. So that's how we can kind of get those two to mix. And this here is a spirit burner, and you kind of have the alcohol here on the bottom, and it kind of soaks up this pipe there, this little rope, and then you can light the top of it, and that is a spirit burner. And so now the final part within alcohols is fermentation. And fermentation is a way in which we can make alcohols from sugar. So we can go sugar, and it's converted to ethanol and carbon dioxide, like so. And this fermentation process uses an enzyme as a catalyst, a biological enzyme as a catalyst. And that enzyme is yeast. So this process uses yeast, and it converts sugars to ethanol. It also produces carbon dioxide. And when this process happens, this ethanol that we make is aqueous, which means it's dissolved in water. The best conditions for this process to work, because it uses a biological enzyme as yeast, needs to be around 37 degrees Celsius. It needs to be slightly acidic, and there needs to be no oxygen for this process to occur. So anaerobic conditions. Any changes or deviations from the temperature and from the optimum pH condition will cause a denaturation of the enzyme, and that will decrease the rate of reaction. So we won't yield as much ethanol as we expect it to. And that is part 3 of organic chemistry. For the next part, we will be moving on to carboxylic acid. To test your understanding, please have a go at these practice questions below, and I will see you in the next part. Bye.